Welcome to Evo AI, where we navigate the intriguing evolution of artificial intelligence. I'm your host, Bogdan Janku, and in this series, we'll explore how artificial intelligence is transforming the way we work, innovate, and grow. From small startups to corporate giants, we'll unravel the mysteries of AI, uncovering insights, strategies, and the real-world impact on our everyday lives. Whether you're in sales, finance, marketing, human resources, or just curious about artificial intelligence, Evo AI has something for you. Welcome back, dear listeners, to another episode of Evo AI, where we decode the intricacies of the tech world. Today, our spotlight is on deep learning. If you think it's just another phrase tech people throw around at dinner parties, just stick around. We're about to dig deep. No pun intended here. By the way, before I forget, if you like our podcast and want to know more, please remember to subscribe on our website on evoai.ai and follow and subscribe to our Spotify, iHeartRadios, Amazon, YouTube, and Apple channels. Now let's get this straight. Deep learning is not a fad. It's a groundbreaking subset of machine learning, which itself is a field of artificial intelligence. In simple terms, it's teaching machines to learn from data, but it does so in a way that tries to mimic human learning. Intrigued yet? Well, deep learning employs what we call neural networks, and not just your run-of-the-mill networks. We're talking about multi-layered neural networks. Picture a digital recreation of the human brain, if you will, simplified and specialized to learn from data. The term deep in deep learning refers to the layers involved. Each layer filters information, starting from the most basic features and gradually getting more abstract as we go deeper. It's like peeling an onion, layer by layer, to get to the core of complex problems. Let's say we're teaching a machine to recognize a cat. The first layer might detect edges and shapes. The next layer recognizes whiskers and tails and so on and so forth until the final layer says, well, hello, that's Mr. Whiskers. If you're wondering about the mathematics involved, just hold tight. The concept is rooted in many things like linear algebra, calculus, and probability theory. But why is it a big deal, you ask? Well, because traditional computing has limitations. There are tasks that require an enormous amount of nuanced understanding, something traditional algorithms struggle with, but deep learning excels in. Consider voice assistants. Early versions could hardly understand accents or dialects. Deep learning models have now significantly improved this, allowing for more natural interactions. If you've ever asked Siri or Alexa to play your favorite tune and they got it right, you've got deep learning to thank. So here you have it. Deep learning is not just a tech buzzword. It's a transformative technology that's reshaping industries and improving our quality of life. And guess what? We're just getting started. Strap in as we dive deeper and deeper into this fascinating world in the segments to come. Let's turn back the clock to the 1950s. The genesis of artificial neural networks was largely inspired by neuroscientists and early computer scientists. One key figure was Frank Rosenblatt, who introduced the perceptron model. This was the foundation stone, but due to computational limitations, it had its drawbacks. The perceptron was simplistic. It could only solve linearly separable problems. Think of it as trying to fit a straight line through a cloud of many points. It works sometimes and it fails spectacularly other times. Moving into the 80s, we come across the concept of backpropagation, popularized by Geoffrey Hinton and others. This algorithm was a game changer for training multi-layer networks, essentially teaching them to minimize errors and improve performance. Backpropagation uses calculus to adjust the network's internal parameters, fine-tuning it iteratively. It's what enables a network to go from barely recognizing shapes to actually identifying objects in an image. As we approached the late 90s and early 2000s, computational limitations were still a major roadblock. Most computers just didn't have the horsepower to train large neural networks effectively. Well, imagine like trying to run a marathon while wearing flip-flops. You could do it probably, but it wouldn't be efficient, it wouldn't be pleasant at all. Now let's enter the world of graphics processing units, or GPUs. These hardware advancements in the 2010s dramatically accelerated the computation needed for large-scale data analysis. They opened the floodgates for the deep learning boom we've experienced today. Key to this era was the development of techniques like convolutional neural networks, or CNNs for image recognition, and recurrent neural networks, or RNNs, for sequence analysis, language translation, for example. CNNs excel at handling visual data and identifying features like edges and textures, while RNNs are masters of sequential data, capturing temporal relationships that simpler models miss. And we can't overlook the role of data and software frameworks in this narrative. With the advent of big data, deep learning algorithms now had the rich, diverse data sets they needed to train on. The more data we could feed into these algorithms, the better they performed. It's like they were running on data steroids, really. Big data isn't just a lot of data. It's diverse and high velocity, streaming in real time from various sources like social media, maybe sensors and more. It provides the neural networks with a comprehensive training ground. On a software front, frameworks like TensorFlow and PyTorch have democratized deep learning. They offer pre-coded layers, training loops, and other essential elements, streamlining the development process. So now, you don't have to be a computer science prodigy to get into this field. These frameworks also offer compatibility with GPUs, enabling faster calculations. This brought down the barrier to entry, allowing more researchers, more engineers, and even college students to experiment and contribute to the field. In conclusion, deep learning's history is a fascinating blend of intellectual pursuits, technical advancements, and computational power, all culminating in the vast landscape we see today. We've come a long way from Rosenblatt's perceptron, hurdled over the computational barriers, and we're now standing at the edge of what seems like an ocean of possibilities. The evolution of deep learning is not just a tale of technological advancements, but also a story of community contribution and growing accessibility. It's a multidimensional saga of innovation that's redefining what we thought machines could do. Let's explore now the mathematics and algorithms that enable this transformative technology work. We're about to delve into the nuts and bolts of deep learning, the math and the algorithms that make it tick. But don't worry, I promise you won't feel like high school calculus. First off, let's talk about the cornerstone of neural network training, loss functions. Simply put, a loss function measures how far off our model's predictions are from the actual results. The goal: minimize this loss during training. Common types of loss functions include mean squared error for regression tasks and cross entropy for classification. They provide the quantifiable metric that guides the learning process. Next in line, optimization algorithms. You've probably heard of gradient descent. It's like the GPS of deep learning, really, helping us find the shortest route to the lowest loss. In particular, stochastic gradient descent, or SGD, and its variants like ADAM or RMS-prop are commonly used. These algorithms dynamically adjust learning rates, essentially fine-tuning the neural network more efficiently. But what about the architecture of these networks? For that, we use layers, lots and lots and lots of layers. In deep learning, the most popular types include dense or fully connected layers, convolutional layers, and recurrent layers. Each type serves a specific purpose. Dense layers are good for straightforward tasks. Convolutional layers excel in handling images, and recurrent layers are great for sequential data like time series or natural language. Let's not forget about activation functions. These decide whether a neuron should fire or not. ReLU, sigmoid, and tan are some of the stars of this show. Activation functions introduce nonlinearity into the system, allowing neural networks to learn from the error and make adjustments. Without them, neural networks would never perform at an acceptable level. Now, before we wrap up this segment, let's touch on regularization. Ever heard of overfitting? Well, that's when a model is so eager to impress you, then it practically memorizes the training data but stumbles when it's faced with new information. Techniques like dropout, L1 and L2 regularization are used to prevent this overfitting. They act as a form of control, ensuring the model generalizes well to new, unseen data. We've covered the basics of what deep learning is and its historical context, and also the mathematics and algorithms that underpin it. Now let's dive into the architecture that powers deep learning, and that's artificial neural networks, or RNNs for short. At its core, deep learning is an advanced form of artificial neural networks. While basic neural networks might have a single hidden layer between the input and output, deep networks can have dozens or even hundreds of these layers. This architectural depth enables them to model incredibly complex relationships. These additional layers are not just for show, they need it. They each perform specific functions. The early layers might focus on low-level features like edges in an image, while subsequent layers interpret these edges to recognize shapes, and even further layers might recognize entire objects based on these shapes. In essence, deep learning networks are a refined version of artificial neural networks, fine-tuned to handle more complex tasks. They are constructed with multiple types of layers: convolutional layers, pooling layers, and fully connected layers, to name just a few. Each type of layer has its unique role. For example, convolutional layers are exceptional at spatial hierarchy and are usually employed in image-related tasks. Pooling layers reduce the dimensions of the data, making the network faster and less prone to overfitting. Now some of you might wonder, why do we often draw parallels between these networks and the human brain? The reason is structural resemblance. Just like the neurons in our brain, these networks consist of interconnected nodes that transmit and process information. Both biological neurons and artificial neurons have inputs, a processing stage, and outputs. However, it's important to note that while inspired by biology, the artificial models are a simplified approximation and cannot capture the full complexity of biological neural systems. There are also specialized variants of neural networks tailored for specific tasks. Convolutional neural networks, or CNNs, have shown excellent performance in image recognition. Recurrent neural networks, or RNNs, excel in handling sequential data like time series analysis or language modeling. In summary, deep learning leverages complex, multi-layer neural network architectures to perform tasks that range from object recognition in images to natural language understanding and beyond. In the next segment, we'll go even deeper into the types of architectures and how these networks are trained. So please stay tuned. Now that we've laid the groundwork on the architecture behind deep learning, let's focus on the specific types that are making waves in various industries. Our two big stars of today are the convolutional neural networks, or the CNNs, and the recurrent neural networks, or the RNNs, as we described them before. First, let's talk about CNNs. These networks are particularly skilled at handling tasks relevant to visual data like image and video recognition. CNNs have layers called convolutional layers that apply a set of filters to the input data. These filters can recognize patterns such as edges and textures. As data passes through additional layers, these patterns become increasingly complex, allowing the network to recognize higher-level features like shapes and eventually full objects. On the other side, we have RNNs, which are exceptional at tasks that require understanding sequences or time series data, such as speed recognition and natural language processing. What sets RNNs apart is their ability to consider past information in their calculations. They have loops that allow information to persist, effectively giving the network a form of, if you want, memory. This is crucial for understanding context in language or trends in time series data. You might also hear terms like long short-term memory networks, or LSTMs, and gated recurrent units, or GRUs. These are variations of RNNs designed to address some of the shortcomings of standard RNNs, like the vanishing gradient problems. The vanishing gradient problems occur when the network is too deep, causing the updates during training to become exceedingly small. LSTMs and GRUs use gates to control the flow of information, making them more effective for tasks that require understanding longer sequences. Another fascinating development is the rise of generative adversarial networks, or GANs. These networks are set up as a kind of dual between two subnetworks, a generator and a discriminator. They're especially good at generating new data that mimics a given set. The generator creates fake data while the discriminator evaluates it. Over time, the generator becomes increasingly skilled at producing realistic data, making it harder for the discriminator to tell the difference. This setup has proven highly effective for tasks like image generation, data augmentation, and even art creation. These are just a few examples of the rich landscape of deep learning architectures, each tailored for specific types of problems. As the field advances, we're likely to see even more specialized types emerge, optimized for increasingly complex tasks. We've ventured through the types of deep learning architectures. You're probably asking now, so how do these intricate models actually learn? Well, you see, these networks aren't born smart. They have to be trained, much like how we humans learn from experience. Training a deep learning model involves feeding it a lot of data and letting it adjust itself based on the errors it makes. This process of adjustment is often managed through a method called backpropagation. Essentially, backpropagation calculates how far off the model's predictions are from the actual results, and it uses this loss to update the model's parameters. The goal is to minimize this loss. Now, minimizing loss sounds like something we all want in life, doesn't it? In the realm of deep learning, though, various techniques are used to achieve this, like the gradient descent. The gradient descent is an optimization algorithm that adjusts the model's internal parameters in the direction that minimizes the loss function. It's like rolling a ball down a hill to find the lowest point. That's where your model wants to be. But wait, don't go anywhere, because there's more. Loss functions and optimization algorithms can differ based on the task at hand. For example, for classification problems, we often use a cross-entropy loss, while regression tasks might use mean-squared error as the loss function. The choice of loss function and optimization algorithm can significantly impact the model's performance, so it's crucial to pick the right tools for the job. And here's something else to chew on. Training these models is computationally expensive. We're talking really heavy-duty number crunching that often requires specialized hardware like the GPUs. GPUs, as we said, graphic processor units, are exceptionally good at handling the parallel computations needed for training these models. Their architecture allows for faster matrix operations, which is a core part of how these models learn. In summary, training a deep learning model involves a mix of calculus, optimization techniques, and yes, some very robust hardware. But the payoff is a highly capable model ready to tackle complex problems. Now, we've been on a deep learning joyride path so far, and it's been great, but every ride has its bumps. So please buckle up as we hit the challenges and ethical curves that this tech brings along. So let's start by digging in the black box concept, a term you might have heard thrown around a lot. But what does it mean? In deep learning, the black box refers to the lack of transparency in how these neural networks make decisions. You input data on one side, get results on the other, but what happens in between is often indecipherable. Think of it like a magic show. You see the magician putting a rabbit out of the hat and then pull out a dove, maybe. Cool trick, but how did it actually happen? Specifically, deep neural networks have so many parameters, sometimes in the millions or even billions, that even if you looked at them, they wouldn't make much sense to a human observer. This complexity allows them to learn from data exceptionally well, but also makes them incredibly hard to interpret. Now, why should you care about this black box? Well, if a deep learning model misdiagnoses a medical condition or maybe deny someone a loan, we need to understand why to correct it and make it better. This is especially problematic in industries that require accountability and traceability, like healthcare, finance, and the judicial system. Understanding why a decision was made is crucial for validation, improvement, and sometimes legal compliance. Moving on, we've already sung the high praises of data, but let's face it, acquiring good, unbiased, labeled data, it's easier said than done. These algorithms require a huge volume of high-quality data for training. Collecting and annotating this data can be both costly and time-consuming. The computational conundrum that we all have. Well, these models are not just smart, they're energy sinkholes. Training a deep network is computationally intensive. We're talking really high-grade GPUs and TPUs that not only cost a pretty penny, but also gobble up electricity like there's no tomorrow. And finally now, the ethical jungle. Using deep learning in areas like the military and surveillance is a hot potato. Who is accountable if something goes wrong? Is it the developers, the users, or the decision makers who implemented it? This lack of clear responsibility makes ethical considerations even more critical. So we talked about where deep learning is at the moment, but let's switch gears and focus on where it's going. There are some mind-boggling innovations on the horizon, folks. Now, if deep learning is the engine that powers so much of AI today, imagine what advancements in that engine mean for the broader field of artificial intelligence. As deep learning gets better, the AI applications that rely on it will become more advanced, more efficient. Take the example of transfer learning. This technique allows us to apply knowledge learned in one domain to another domain. As this becomes more refined, the time needed to train AI for specific tasks will reduce dramatically, allowing for quicker deployment and less computational costs. And it doesn't stop here. Ever heard of zero-shot learning? This is where a model can correctly make inferences about data it has never seen during training. Imagine an AI that can adapt to new situations on the fly. That's really revolutionary. Zero-shot learning will make it possible for AI models to generalize better. This is particularly crucial for real-world applications where the input data can be incredibly diverse and unpredictable. Another remarkable trend is the potential integration of deep learning with quantum computing. This could be a game changer. Quantum computers can handle complex calculations way faster than classical computers. The quantum bits or qubits can be multiple states at once, allowing for more complex and quicker calculations. Pairing this capability with deep learning algorithms has the potential to solve problems that are currently computationally intractable. As we wrap up our conversation about what's coming down the pipeline, let's talk about something straight out of the science fiction novel: enhancing human brains with deep learning algorithms. Yep, you heard that right. Companies like Neuralink are at the forefront of this exciting intersection between neuroscience and artificial intelligence. Imagine a world where deep learning algorithms could enhance your cognitive abilities directly. Neuralink's ambitious projects aim to interface the human brain with computers using specialized chips. The role of deep learning here is vital for decoding complex neural patterns and translating them into actions, into thoughts, or even enhanced learning and memory capabilities. This isn't just about downloading a foreign language into your brain overnight, although that may be pretty cool, let's face it. It's about the potential to tackle neurodegenerative diseases, enhance human cognition, or even pave the way for a sort of symbiosis between humans and artificial intelligence. The algorithms would need to be incredibly sophisticated and capable of real-time analysis and interpretation of vast amounts of neural data. This is where advances in deep learning algorithms for sequence modeling and real-time analytics could play a pivotal role. As we look ahead, the intersection of neuroscience and machine learning continues to be a goldmine for innovation. As we better understand how the brain works, we can create neural networks that are far more efficient and capable than what we have today. Just as convolutional networks mimic the visual cortex, future neural network architectures might replicate other human cognitive functions like memory and attention mechanisms, making them more versatile and effective. So while deep learning has its fair share of challenges, the future looks bright. As the technology matures, its impact on AI will be profound, breaking new ground and setting new paradigms in how machines can assist, augment, or even exceed human capabilities. Now, we've traversed the complexities and applications of deep learning, but what does the future hold? If you're expecting flying cars and robot butlers or whatever, well, you might have to wait a little bit longer. But the leaps in deep learning are nothing short of revolutionary. One future trend that's catching everyone's eye is lifelong machine learning. Instead of training a model just once and deploying it, these models will learn continuously, adapting to new data as it comes in. This is a significant step in creating AIs that can adapt and evolve, reducing the need for constant human intervention to retrain models. Techniques like elastic weight consolidation help in retaining the learned information while adapting to new tasks, making the models far more resilient and versatile. Another area worth noting is unsupervised learning. Right now, most deep learning requires tons of labeled data to train a model. But what if a model could learn by just observing, similar to how a human child learns? Methods like generative modeling aim to achieve this by enabling the machine to understand the underlying structure of the data. The machine can then make educated guesses or predictions even when dealing with unfamiliar scenarios. Finally, let's not forget the ethical aspects. As deep learning systems become more integrated into our lives, questions about data privacy, algorithm bias, and ethical AI will become more pressing. Solutions like differential privacy and adversarial training are being developed to tackle these issues, adding layers of security and fairness, maybe, to deep learning algorithms. So hold on to your seats, folks, because the Deep Learning Express is only picking up speed. It promises to not just transform technology, but redefine our very understanding of intelligence, both artificial and human. And there we have it. That's it for today's episode of Evo AI. We've covered the history of deep learning and how it works, and we've peered into the near future at how artificial neural networks and deep learning will enhance the power of AI. We hope you found it as informative as we did putting it together for you. If you enjoyed this episode and want to hear more about the fascinating world of technology and artificial intelligence, please make sure you subscribe to our website, evoai.ai, and follow us on our Spotify, Amazon Music, and Apple channels, and please leave us a review. Well, that's a wrap of today's episode of Evo AI. We've delved into the fascinating world of artificial intelligence, unlocking insights that are changing the face of business today and tomorrow. But the exploration doesn't end here. There's always more to discover. Well, I'm Bogdan Iancu, and this has been Evo AI. Together, we're part of something bigger, much bigger, a movement towards understanding, innovation, and growth. Well, if you enjoyed our journey today, don't forget to subscribe, and please join us again as we continue to explore the future of AI in business. Until next time, keep evolving.